Section 6.3, number 12, talks about teachers' salaries in North Dakota. It says the average teacher's salary in North Dakota is $37,764. Assume a normal distribution with sigma equal to $5,100. A. What is the probability that a randomly selected teacher's salary is greater than $45,000? So as we do this one, let's figure out what we know first. It says the average teacher's salary is in North Dakota is $37,764. That is our mu. And now that we're looking at the central limit theorem, which also involves another type of mean, we have to figure out which one is mu and which one is our x bar. So to keep in mind, mu is our population average or mean, and x bar is our sample average or mean. So they're talking about North Dakota here. For A, it really doesn't matter, but we know this is mu, not x bar. For B, it says, what is the probability that the sample mean is greater than 38,000? So that already tells us that 38,000 is x bar, and therefore 37,764 has to be mu. That has to be our population average. So we know that's our mu. So mu is equal to 37,764. And they also tell us it's normally distributed, which is good, and sigma is equal to 5,100. So sigma is equal to 5,100. So part A is very similar to 6.2. This one doesn't really involve the central theorem. They want to know the probability that a randomly selected teacher's salary is greater than 45,000. So our 45,000, that's our x. X is 45,000 and greater than. So when we draw a distribution here, this is in terms of x. Let's have our z distribution also. So for z, our mean is 0, or our mu is 0, but in terms of x, it's our 37,000. And our x here is 45,000, which is greater than 37,000, so that's going to the right, 45,000. And they want greater than 45,000, so greater means shade to the right. So we can copy that down here, and we shade to the right, but we need to find our z value first. So remember your formula, z is equal to x minus mu over sigma, which means 45,000 minus mu is 37,764 divided by sigma, which is 5,100. Plug that in our calculator. Let's see what we get. So we get z is equal to 1.42 because the 8 rounds that 1 up to a 2. So here we have 1.42. Now let's erase this so we have a little more room. So now that we have our z value, we need to find this area. However, when we look in our graph, when we look in our chart, it gives us the area to the left. But we know how to figure out the area from the right. We just subtract that area from the left from 1. So let's look that up in our chart here. 1.42, and it's positive number, so we go to our positive distribution. 1.4 is here, 0.02 is here, so we have 0.9222. That's our area to the left. So this is 0.9222, and we want the area to the right. So we do 1 minus 0.9222, and that gives us 0.77, there's a 0 in there, 0.0778. That's our probability for part A. If we were to plug that in our calculator, let's plug that in. So we have our lower will be 1.42, upper is infinity. So let's do that, 1.42 to infinity. Second vars, normal CDF, lower is 1.42, comma, upper is infinity. So 1 times 10 to the 99, close parentheses, and we get 0.0778, which is precisely what we got here. And now for B, let's look at B. It's a little bit different. Part B, you're going to use the central limit theorem for. And the way you know that is because they give you, let's use a different color. Let's use blue. So you know you're going to use the central limit theorem if they give you sample mean and a sample size. Remember, sample size, like out of the entire population of North Dakota, you're going to sample 75 teachers. So that's how you know what your N is. So N is 75, that's our sample size. And the sample mean, or sample average, same thing, X bar is 38,000. That's important to distinguish the difference between central limit theorem and section 6.2 because, like I said, you have N and an X bar versus just an X. So let's draw our distribution. Here's in terms of X. And here we have 37,764 as our mu. And our X bar is 38,000. That's bigger, so it's going to be on the right side. 38,000. And they want greater than 38,000. So we're going to shade to the right. Now basically from here, the steps are pretty much the same as 6.2, except you have a different Z formula. Now our formula for Z is equal to X bar minus mu times the square root of N over sigma. So let's calculate Z. So Z is equal to X bar is 38,000 minus our mu, which is 37,764 times N, the square root of N, which is 75 over sigma, which is 5,100. Now remember when you're writing this down and when you put in your calculator, don't forget your parentheses. Those are very important, otherwise your calculator will do this first. And we want to do our subtraction first. So make sure you put in those parentheses. It's very important. So let's do that in our calculator. 38,000 minus 37,764 times the square root of 75 divided by 5,100. We get Z is equal to 0.40. So let's write that up here. It's equal to 0.40, and I'm going to erase this so we have a little more room here. So let's draw our Z distribution now. Remember, mu is always in the middle. Mu is 0 when you're talking about Z. And our Z is now 0.40, and we're still shading to the right. That hasn't changed. And we want, since we want the area to the right, When we look up at our chart, it only gives us the area to the left. So let's look up that in our chart, 0.4. So 0.4 is positive. So we go to 0.4 and 0. So 0.6554 is the area to the left. So 0.6554. And we know the area under the entire curve, once again, is 1. So we do 1 minus that to get the area to the right. So 1 minus 0.6554 will give us the area to the left, which is 0.3446. That's our area to the left, 0.3446. We can also use our calculator for this part. We would have our lower normal CDF to be 0.40, and our upper is going to be infinity. So let's go to our calculator. We have second vars, normal CDF. Our lower is 0.4, comma, our upper is infinity, so 1 times 10 to the 99 power. And we get, look at that, same thing, 0.3446, which is same thing.